A very good afternoon to Dr. Zhang. Our group will be presenting on glucose biosensors, and so I'll begin with the introduction of biosensors. As you can see from the slides, this is the structure of the biosensors. The biosensors has three main components, which is the biological recognition element. These elements are highly specific towards the biological material analyzed that we are going to test. And then the second one is the transducer, which transduces the signals from the biological targets to electrical signals. Lastly is the amplification and the detection, which produce the discrete or continuous digital electrical signal that is proportional to the specific analyte. As you can see from the flow, it's from the analyte, and then the analyte will go through the bioreceptor, and then after the bioreceptor, the signal will be transduced into electrical signals and then amplify and also detect by a specific machine. And then the next slide is also the same principle of the biosensors. This is the simplified version. As you can see, the analyte will go through the bioreceptors, and then the bioreceptors will produce the signal into the transducer, and then the transducer will transduce the signals into electrical signals, and then lastly is amplified to see how is the results. And then why our group choose glucose biosensor is because diabetes is becoming a most common endocrine disorder of carbohydrate metabolism. So actually there are many tests used to diagnosis and management of patients with diabetes. But then because of this recommendation of maintaining the normal blood glucose level, there are a series of suitable glucose measuring device has been developed. So glucose biosensors are one of the developed devices used to observe the concentration of the glucose in one of the patients. Our group will be presenting more focus on two types of biosensors generally, which is the fluorescence glucose biosensors and the amphometric glucose biosensors. Fluorescent glucose biosensors are the devices that measures the concentration of glucose in the diabetic patient by the means of sensitive proteins that relates to the concentration by means of the fluorescence. Fluorescence is actually a property that present in a certain molecule which is called the fluorophores, in which they will emit photons shortly after absorbing one with the higher energy wavelength. Fluorescence refers to the emission of light by a substance after it absorbs light. This phenomenon occurs when the incoming light strikes on a molecule or a structure with the fluorescent property, and then they will promote the electron to a higher energy level. The excited molecule will loses its energy by emitting the light, and so as we will see the fluorescence. For the sensing purposes, this property is already is used in the combination with the biomolecule, such as the protein, which undergo conformational change upon the ligand binding, changing the distance between the two labeled on this protein, or in the competition assay, in which the analyte has to compete with a known concentration of a fixed labeled ligand for the labeled binding site of the protein, and therefore the foster resonant energy transfer between the binding site and the competition ligand decrease when the analyte concentration is increased. So you can see from the slide, when there's a low concentration of a glucose concentration, the results will be a low fluorescence, and then with a high concentration of glucose, there will be high fluorescence as a result. The next slide will be the illustration of the assay chemistry and the FRET sensing principle. This sensor is actually characterized by an epic fluorescence setup with a optical fiber spectrometer. In this setup, the light from the LED source with the central wavelength of 590 nanometers passes through a 50 nanometer excitation filter centered at the 560 nanometers, and then through a beam splitter, and finally were coupled to the fiber by the lens in order to excite the assay chemistry. The resulting fluorescence from the assay is collected by the fiber and then passes through the beam splitter and a long pass of emission filter with the 610 nanometer wavelength to finally reach the spectrometer, and this will result the fluorescent result lah. And next will be the M4 glucose biosensor. This glucose biosensor is actually the most common device that is commercially available and widely studied over like a few decades. The atmospheric sensors are used by monitor the current generated when the electrons are exchanged either directly or indirectly between the biological system and the electrode. This how could we say, this biosensor actually uses three types of enzyme, which can use three types of enzyme, which is the hexokinase, glucose oxidase, and also the glucose 1-dehydrogenase enzyme. But these enzymes are actually differ in the redox potential, cofactors, or turnover rates, and also the selectivity for glucose. So from what they observe is glucose oxidase is the standard enzyme more suitable for these biosensors because it is relatively higher selectivity for glucose. And also glucose oxidase is also easy to obtain and is cheap and can withstand a greater extreme of pH, ionic strength, temperature, and than many other enzymes. Let's go back to the previous slide, and then this is how the amphoteric glucose biosensor looks like. Actually, this biosensor function by the production of a current when a potential applied to both of the electrodes, which I already mentioned before. They generally have the response time, dynamic range, and sensitivity similar to the potentiometry biosensors. As you can see, this biosensor actually consists of a platinum cathode, and at which the oxygen is reduced, and then a silver chloride reference electron. How does it actually works is that when a potential of 0.6 volt relative is applied, and then the relative to the silver chloride electrode is applied to the platinum cathode, a current proportional to the enzyme concentration is produced. Normally, these two electrodes are bathed in a solution of a saturated potassium chloride and is also separated from a bulk solution by an oxygen permeable plastic membrane. So for the further mechanism, my other group mates will be further explaining about it. Thank you.
I will be discussing about the mechanism of glucose biosensor. There are two types of glucose biosensor that I will be discussing. The first one is the environmental, and the second one is fluorescence. For the first one, environmental glucose biosensor, it uses the enzyme glucose oxidase to catalyze the glucose by using molecular oxygens. So the product will become gluconolactone and the hydrogen peroxide. There are two types of reactions that involve in this glucose biosensor. The first one is the reaction of glucose with the enzyme, but before that, the glucose oxidase will require a redox factor to act as an initial electron acceptor, that is flavin adenine dinucleotide. It will be reduced into FADH2 after the reaction with the production of gluconolactone. For the second reaction, the FADH2 will be regenerated by reacting with the oxygen. Thus, hydrogen peroxide will be produced with the FAD. In this case, the hydrogen peroxide will oxidize at the platinum electrode. The number of electrons that transfer at the electrode surface was directly proportional to the number of glucose present, for example, in the blood. Next, I will discuss about the fluorescent glucose biosensor. In the glucose biosensor, there are two components. The first one is the acceptor, and the second one is the fluorophore, or what we call fluorescence component. When there is the presence of glucose, the glucose will bind to the acceptor, and this will induce a structural change that brings the acceptor and the fluorophore farther apart. In this case, the fluorescent resonant energy transfer, we call as FRED, will decrease. It is defined as the energy transfer between two light-sensitive molecules. So when the fluorescent resonant energy transfer is decreased, there's also decrease of electron sharing between the acceptor and the fluorophore, and this will result in the increase of luminescence in the fluorophore. However, in the absence of the glucose inside the biosensor, there's an increase in the fluorescent resonant energy transfer. This is because the acceptor and the fluorophore has developed a steric and electronic interaction between this group. So there is a decrease in the luminescence in the presence of the light. And this is the summary of the fluorescent glucose biosensor that I have just mentioned.